Hello, my name is Rothmeier and today I will present my work Time to Shine, fine-tuning object detection models with synthetic adverse weather images. This work was done at Technische Hochschule Ingolstadt together with the Charisma Institute, Technical University Munich and the project AIC. So when automated vehicles are confronted with adverse weather conditions, such as rain, fog or snow, most sensors and algorithms stop working correctly or fail completely. In clear weather conditions, however, these sensors and algorithms work properly, as algorithms are trained mostly on good weather datasets. As we see on the left, these are vehicles detected by an algorithm in clear weather. So we see a car, another car, a bus, and all the vehicles in the background. On the right, we see the expected results of a detection in rainy weather conditions. Car, another car, and another car. However, when running a faster RCNN model on the image, we get the following detection. Bench. Even if it is clearly a police car for a human observer, the other cars are not detected at all. The problem really is that the detection degrades in adverse weather. In our work, we aim to improve robustness of detection algorithms. So what we are doing is first to create a large bunch of text prompts that describe driving scenarios in adverse weather conditions. We wanted them to be highly diverse and used ChatGPT as a tool for this. An example for a prompt is below. Next, we fed the text prompts to the Midjourney AI and synthesized image data in snow, fog and rain conditions resembling driving scenes. The results from this step is a dataset of approximately 20k images containing extreme adverse weather conditions. In the next step, we labeled all vehicles in the images to use them as training data. With this training data, we fine-tuned 4 different detection models to see whether the robustness towards adverse weather improves. This slide shows some of the results of the generated and labeled images. On the left, we see images of vehicles driving in fog conditions, in the mid vehicles in rain conditions, and to the right vehicles in snow conditions. The images are difficult to differ from real images and show high diversity. We started to evaluate 4 different detection models, faster RCN, FCOS, RetinaNet and SSD, in the domains fog, rain and snow. Every detection model is fine-tuned with data from its respective domain, for example fog, and tested on dataset from the fog domain, rain tested on the rain domain, and snow tested on the snow domain. We compare the average precision of fine-tuning on only clear weather images, on augmented images, and fine-tuning with our synthetic dataset we created in our work. We see an improved robustness of more than 13% for fog and more than 8% for snow compared to fine-tuning only on clear weather images. The average precision for rain remains mostly similar. We think the reason for this is that the test set's not containing extreme rainy conditions and resembles more clear weather conditions. We also compared the results when fine-tuning with standard augmentation techniques. For this we chose the augmix augmentation. Our synthetic data clearly shows better average precision for all conditions. In the following we did an assessment on the robustness specifically towards fog conditions. For this we chose the cityscapes dataset and the cityscapes foggy dataset with 3 different fog intensities. The cityscapes foggy dataset is a dataset with light fog, medium fog and strong fog. We compare a baseline model that is pre-trained on the COCO dataset and has no fine-tuning, then a model fine-tuned with a simple fog augmentation method, and a model fine-tuned with synthetic fog data. We did the evaluation for faster RCNN, FCOS, RetinaNet and SSD. For all algorithms tested, we see an improvement when training with synthetic fog data. In strong fog conditions, we see major improvements compared to baselines. In this evaluation, we were interested how different dataset splits between real and synthetic data affects the average precision of detection models on our test datasets. For this, we used different splits of real and synthetic data. We used 1,500 labeled synthetic images and 1,500 labeled clear weather images and incremented the amount of synthetic data in steps of 20%. So starting with 1,500 clear weather images only, then 1,200 clear weather images and 300 synthetic images, up to 1,500 synthetic images only. In our evaluation, we see that an increase of synthetic data improves average precision up to an amount of 80% for fog, rain and snow. In clear weather conditions, we get worse with an increase of synthetic data. When using all 1,500 synthetic images for fine-tuning, we observe a huge drop in average precision for every domain. To sum up our work, we found that synthetic driving images with adverse conditions are indeed capable of improving the robustness of detection models. Further, we see a high degree of realism and diversity in our generated dataset that is hard to differ from reality. Often it is not possible to collect data of certain scenarios. Adverse weather conditions is one of these examples difficult to collect in reality. However, there exist more edge case scenarios that are challenging or ethically difficult to produce. Moreover, the collection of this data is far less time-consuming than doing real-world tests. Some drawbacks of this method are that images not always adhere to semantic correctness. So we have, for example, cars driving in false directions or deformed objects that may resemble a car. Also, the synthetic data requires still manual annotation, which is often not easy for adverse weather images, and requires lots of manual effort. The approach is further limited to camera images for the moment and cannot be applied to automotive sensors like LiDAR and radar. Thank you for your attention. If you have further questions, please feel free to send me a mail.